This is a Chapter 5 continued, the second lecture on Chapter 5, and we're continuing a discussion of pulse methods in voltammetry and polarography. And as we were finishing last time, we were discussing the response for potential steps to arbitrary positions on waves. And so we were doing essentially a reversible kinetics case, which again, reversible suggests that we've got Nernstian type behavior at all times, equilibrium behavior at the electrode surface. And we just demonstrated that by stepping out and stepping back, we could get these sampled current voltammograms that gave us the exact shape as we'd calculated previously using the simple ideas of mass transfer coefficients and so on. The idea was that we would take our voltammograms, plot them versus time, and we could get a family of voltammograms such as this. And if we sampled at a particular time tau at various values of what we're going to call E theta values, we could get this family. And so the plot would be down here, E theta. And remember, we define theta as equal to e to the nf over RT, e minus E0 prime, and the squiggly e was the ratio of diffusion coefficients to the square root power. As usually, we're assuming that the diffusion coefficients are pretty close to 1, or that ratio would be pretty close to 1. In other words, that DO and DR are pretty close to 1. And when we take the square root, they're even closer to 1 usually, even if they're off a little bit. Although we have some cases where there's significant differences in those values, and that will cause some deviations. Under those conditions, as I said, we get the sampled current voltammogram, which is for any particular tau would be appropriate. So for a tau, and then if we changed it to a different tau value, let's call it tau prime, we would get a lower value of the wave height, as you'd expect. And again, those are exactly analogous to the waves that we saw before, that we derived before. Now for any fixed time tau, we can say that our I as a function of that tau is equal to I sub d tau 1 minus E theta. And remember, ID is the current that we would get when we're at the very top here. So this would be ID tau. In other words, the diffusion limited tau, if you will, the time we're at the very, very top of the wave. Or we can rewrite that to say that E theta is equal to I sub d tau minus I tau over I tau. And that gives us our sigmoidal shape that we expect. So you can plot these waves like that. Now, for current potential curves, we can take this information and then we get values. Since we know that for a reversible system, we're going to get equation like this. Theta then is equal to what we've already written down, except that we've now added the little e to this mix. And so often we will assume the DO and DR, and then we can drop that little squiggly e out of the system, and that gives us what we want to know. But if we don't, we can write it as a more written out form. There's our squiggly E term. Pens are not working very good for me. And we can then write from there that our half-wave potential, the point where we're halfway between the two, can be equal to minus RT NF ln. So, okay. In other words, if we plot our wave up here, there will be exactly at the middle of that wave, we'll get a E1/2 value. And again, that would be a sampled current voltammogram for a particular tau. And then right in the middle, we can say that is E1/2 minus RT over NF ln. So in other words, if we do this voltammogram, we can look at the half-wave potential and make a statement about the E0 for that particular compound. If we're assuming it's reversible, and we're also assuming that we don't have a diffusion coefficient difference in the ratio of the two. Again, usually this term is quite small, so that's not usually a big correction from E0 to E1/2. So usually it's a good assumption if we get the half-wave potential and to make that equal to E0 prime. Okay. We can also test whether the wave that we get is reversible, because we've made the statement, well, we can check and get an E0 from the E1/2 if it's reversible. Well, we might want to check if the wave is reversible to see if that's true. So what we can do is we can plot, for example, E versus the log of ID minus I over I. And this, in fact, works for any sigmoidal current potential wave, not just the sample current voltammograms, but the waves we've also talked about before. And we'll find that we'll get a slope of 2.303 RT over NF, or 59.1 millivolts. 59.1 over n millivolts at 25 degrees C. So if we make this plot of log ID minus any I on the thing as a function of E, we'll get that straight line curve, hopefully, and that should give us a slope of 59 millivolts. And that's easy enough to do now with computers and so on. And so we can check if we say, well, that's E0, well, let's do a plot. Let's check to make sure it's got a straight line at 59 millivolts, and that will tell us. If it's got a slope of, say, 30 millivolts, well, our n is probably not 1. It's probably 2, and we've sharpened that slope up. If we see slopes of, say, 70 millivolts or 100 millivolts, which are common, those would not be reversible waves. They'd either have electron transfer kinetics that we have to consider. In any case, the theory we just derived would not necessarily be appropriate for these sorts of curves. So you want to watch that sort of thing. Make sure that if you're assuming it's reversible, you can check and see if it actually is. There's also something called the Thom's criteria. Thomesh probably is how you say it. A lot of the early analytical work in voltammetry was done by a guy named Hyrovsky, who was Czech, and he won the Nobel Prize for polarography, but a lot of then that school developed from his work, and so a lot of important work in electrochemistry, early work, was developed by the Czechs working in that area. And the Thomesh criteria says that E3/4 minus E1/4 should be 56.1 millivolts. And so E3/4 would be 3/4 of the way up the wave, E1/4 would be 1/4 up the wave, and you can just take the difference between those two, that very simple and quick check. Rather than doing the whole plot, you can just check that for being 56 millivolts. Of course, that would probably be divided by n, too. Now, for a reversible case, we can get E0. We can also should be able to get D0 values. In other words, the diffusion coefficient values also should be able to get concentration values. That assumes we know the other things. So if we want to get D0, we're going to have to know concentrations and number of electrons and so on. If we want to get concentrations, we need to have D0 values and so on. So the other thing that we can get from these things is deviations from equilibrium. If we're looking for situations where the system starts to experience a chemical reaction, we can see that chemical reactions start by a shifting from the equilibrium points. And so our wave shapes will start to shift and become away from the reversibility criteria that we've already established. Okay. All right, so we've got some results here. So far, let's make a little scorecard. And we've seen that we've developed the Cottrell equation, an important result. Where we get the diffusion current as a function of time. Probably should just make that as I, because we've used the ID as the, well, actually it is ID. Sorry. ID, because remember, Cottrell, we're stepping to the top of our current potential wave, and so that, in fact, would be ID. We've developed a theory for the reversible case, where we've got arbitrary steps, and we see that I is equal to ID, which is given by the Cottrell equation, and 1 plus E theta. So a very simple extension to the Cottrell situation. Let's consider now an important case, the general case, the quasi-reversible case. Okay, let's think about what we're doing here. We got O plus n electrons going to R. And so the quasi-reversible case would be the situation where we have forward and back rates are appreciable, but not so slow as to eliminate the possibility of one or the other. Remember, Kf and Kb are linked by a standard rate constant. So a fast Kf is suggesting a slow Kb, and vice versa. So as we make Kf faster and faster, Kb becomes slower and slower. Now, for a reversible case, we're suggesting that Kf and Kb are both rapid enough on the time scale of the experiment that we don't have to worry about them. We've assumed equilibrium is maintained at all times. For a quasi-reversible case, we don't make the assumption that equilibrium is maintained. So we have to then include the rate constants in our expression for the results. Now, as before, we can start with the Laplace versions of our concentration gradients and substituting in boundary conditions that we've used previously. Okay, and C sub R bar X S and usually this is 0 for most of our situations, so we'll leave it at that. And as we've seen from previous derivations, this is a general form of that equation. And our boundary conditions that we've used here, concentration of O at the electrode surface for time equal to 0 is equal to the bulk. And concentration of R at x0 is equal to the bulk. And usually this is approximately 0. So it doesn't necessarily have to be exactly 0 to get basically the same result. So let's put in our general purpose boundary condition. We've used non-general cases before. So in this case, when we only have to worry about electron transfer kinetics, we can put in our general boundary condition that includes electron transfer kinetics. Which says that the current is equal to the diffusion coefficient times the gradient in concentration at the electrode surface, or the flux, times Kf CO at the electrode surface minus Kb C sub r at the electrode surface. And you can recall the form of the Kf and Kb from the previous chapter. Kf is equal to K0 e to the minus alpha NF. And we'll put in N sub A F E minus E0 prime, where F is equal to F over RT. Kb equal to K0, oops, times, I don't know why I got equal there. K0 e to the 1 minus alpha N sub A F E minus E0 prime. Okay, we're using N sub A because we're including the possibility of having a multi-step electron transfer, and so that N sub A is an apparent number of electrons in the process. Basically, it's the number of electrons in the rate determining step. Now we can Laplace transform this above equation. So if we do that, we get diffusion coefficient times CO in the Laplace space Now I'm going to skip some algebra here. It's in the book. I don't see any point in really me going through all these steps again. You can follow along through the book's derivation. But anyway, we can start from that point and get the result that we're interested in, and that says the concentration in the Laplace space of species O is equal to the initial concentration, or the bulk, divided by the S variable plus our initial condition, A is a function of S. And C sub R is equal to that's A sub S. So these A sub S looks, in this case, it looked very similar to what we derive for the reversible case for arbitrary potential steps, but now the boundary condition is different. So we're going to get a different form of the solution. And again, we're taking the derivatives of these, doing some more algebra. Again, I'm going to leave that off because it would take a couple pages and really not that important to do all the algebra in your here right now, but you can do it yourself, I think, at this point. And I would encourage that if you're wanting to really understand things. But we can derive our value of A as a function of S as the forward rate constant divided by the diffusion coefficient, the bulk concentration times the Laplace variable, and a parameter H plus S to the 1/2 power. So this is kind of messy, but H is equal to Kf over D sub O to the 1/2 plus K sub B over D sub 0, D sub R to the 1/2. All right. So knowing that, we can can calculate the current, which is really what we want. We don't really care so much about the bulk concentrations. But let's calculate the current, and we can use the basic form of the current in the Laplace plane as we previously derived. Again, the gradient at the electrode surface. And do the inverse transform, and we get the current as a function of time. Again, exph sub squared t, error function complement, ht to the 1/2. Now that's a little bit messy, really messy. So you could do it now with computers very straightforwardly, actually, calculate the current versus time relationship. Just have to substitute in what the values of kf and kb are. And you can get kf and kb from the k0 value in alpha. And that's all you need anymore. Prior to computers, it was quite a job to make a graph of this sort of thing. We can actually draw a sketch of it. It's not going to be exact, but we can point out one important feature is that rather than the current going to infinity, as we see for a reversible case, stepping out to the ID, we actually get intercept with the axis at some point. And so the current at t equals 0 is equal to NFA KF C0 star. Okay? That makes sense, because remember, we're talking about stepping out, and we've got a non-reversible, well, it doesn't have to be reversible, quasi-reversible case. And so as we step to anywhere along that wave, the only rate that we have to worry about at initial time is the forward rate. The backward rate only comes into play when we have appreciable amounts of C sub r, and none of that's initially present. So that gives us the current. And so it does have that's one way of finding a forward rate constant. It's not really that accurate a way, because as I said, getting the results at very short times is difficult with the potentiostatic limitations, IR drop, and so on. So it would be kind of difficult to get that, but it could otherwise be found. You can actually get the current by doing the evaluation of this equation, the upper equation in the Laplace plane, this one here. And then from that, using the convolution function to get out of it. I think we already drew it. I show in my notes the form of the error function. And something like that for y 1 and 2 goes to 0 at y equals 0, goes to 1 at basically at y is greater than 2. Okay. So now we've done 3 of the cases that we're interested in. Let's do the 4th one. Irreversible case. So what's going on here? Well, we took the reversible case, or quasi-reversible case, a little messy, but not too bad. We can get curves as a function of time for any particular KF, KB result. In the irreversible case, we're talking about O plus NE going to R. And again, we've got KF, KB to worry about. But in the irreversible case, it's irreversible. When we say irreversible, we're usually meaning electrochemically irreversible, not irreversible because R is involved in some following chemical reaction. So we're talking about a reaction in which the backwards rate, Kb, is quite small. And really the only way that works out is if we go back and look at our equation for Kf and Kb. Notice the relationship. If K0 is quite small, then that means that for potentials that are larger than or more negative than E0, we will get some large value of Kf. Okay, so if K0 is not small, then if we make a significantly negative potential from E0, the rate now becomes the mass transfer limited rate. We're limited by diffusion alone. And we won't see any kinetic behavior because we'll be a rate at which is larger than the mass transfer rate, the diffusion rate. So only when we have really slow values of K0 does this irreversible condition start to hold, because the irreversible condition makes the assumption that K sub B is very close to 0. And so only when K0 is small and we've got appreciable overpotential does that case hold. And so, but it happens, it holds actually in a number of cases, so it's a useful situation. If Kb is 0, we can write our H value from the previous result. Since the quasi-reversible case is a general case, we can just take out the parts of the quasi-reversible case that we don't need. And so H is equal to K sub F over D to the 1/2. And we can define a kinetic parameter, and you'll see this lambda used quite a bit in the next chapter or two as a kinetic parameter. Lambda is a dimensionless parameter, which includes the parameters of, which includes the variables of time and rate constant and diffusion coefficient. You'll see that that is a dimensionless result. There's no units on lambda. So lambda increasing suggests that the rate is becoming larger or the time is becoming larger or the diffusion coefficient is becoming smaller. In this case, the current as a function of time is equal to NFA C0 star Kf, stuff we've already derived, but now since H is simple, we substitute in or by using our dimensionless parameter and the diffusion limited result, and we get that. I over ID is a function, F1 lambda is equal to pi to the 1/2 lambda exp lambda squared, error function complement of lambda. Okay. And if we plot that as a function of our kinetic parameter at about 0, -1, -2, 1, 2, and plot our function of lambda, Maybe 1, and so on. We get basically a plot that looks something like that. Not exactly like that, but that would be your error function exponential sort of fighting each other to get the shape of the curve. And basically what this is saying here is this is a long time or fast or large values of kf. So if we do the experiment for a long period of time, our function approaches 1, and we get the basic same result as we got if we're having we get the value identical to I sub d, in other words. If we do very fast rate constants or larger values of k sub f, then we have, again, a value that would be similar to the reversible case. Now, in this case, again, we're talking about irreversible kinetics, so kf can't be so fast that we start to get into the reversible or quasi-reversible regime. So basically, fast kf is limited. We're also going to have somewhat of a long time, or alternately, we could have a small value of the diffusion coefficient, which could happen in, say, a gel or a sort of a semi-solid material, or a solid material even. Okay. So this basically is the shape of the curve. Now, as I said in the notes, for sampled current voltammograms where we're sampling the current for our irreversible wave, and we get a result like this, the lambda is just a function of potential. In other words, because tau is fixed as a time parameter here, kf is a function of potential, and d is fixed. So lambda is basically potential under our sampled current voltammograms. Okay. So what do you see for irreversible sampled curve voltammograms is that rather than having a half-wave potential at E0, the wave is shifted significantly negative, for example, for a reduction process, and the half-wave potential will be shifted away from that. And how much it's shifted away is dependent on exactly the value of k sub f. And that's the situation for all these irreversible waves. They shift out. They basically don't have any change in the shape. Once you have the general shape for the irreversible wave, the basic difference is as kf becomes more and more smaller and smaller, the wave just shifts more and more negative, but maintaining the same essential shape as before.